Hi everybody, here's a supplemental video to finish up Chapter 12. Last week in class we went over the redox reactions involving alcohols. So for example, we saw that we can use sodium borohydride or lithium aluminum hydride to reduce a variety of carbonyl compounds to their alcohol form. And then conversely, we can take an alcohol and we can oxidize it to a carbonyl. However, the type of carbonyl depends on the nature of the alcohol and the strength of the oxidant. So last week we took this example with primary alcohols. We said if you have a primary alcohol, you can do a 2-electron oxidation and end up at an aldehyde, or you can do a 4-electron oxidation and push it all the way to the carboxylic acid. So it's important to remember that alcohols, depending on the strength of the oxidant, can end up at either an aldehyde or a carboxylic acid. This is different than secondary alcohols. Secondary alcohols can only undergo a 2-electron oxidation, at least that we know of right now, to a ketone. We can't push them all the way to the carboxylic acid, at least right now. We'll cover that reaction when we get to third term. And then tertiary alcohols, we can't oxidize at all because we don't have any hydrogens coming off of that central carbon. So last Friday we ended by talking about the reagents that are necessary for oxidations. So let's take a look at the first reagent that we covered. We were looking at forming chromic acid. Somebody did point out a mistake at the end of the lecture where I have an oxygen in the center here. Sodium dichromate should have 2 chromium atoms in the center right there. So now we've got 2 different routes through which we can make chromic acid. We can either mix chromium trioxide, CrO3, or sodium dichromate with strong acid to make chromic acid. Chromic acid is generally just made in your reaction flask. So we took a look at this example with the primary alcohol and chromic acid. With chromic acid, we said you can't stop at the aldehyde, meaning we're always going to end up with the carboxylic acid. It's a really, really strong oxidant, so it's impossible to stop at that intermediate we saw on the previous page. And then with secondary alcohols, we could do an oxidation reaction, but because there's really only one state for it to land on, it's always going to land on the aldehyde, the ketone right here. All right, so let's kind of look at this mechanism in a bit more detail, although the book is kind of vague with it, so I'll stick with the book's explanation. This is often referred to as the Jones reaction. So let's take the example using a secondary alcohol like this, and I'll just show the hydrogen right there for clarity's sake. We know that we're going to be reacting this with chromic acid. And chromic acid looks like this, where we've got 2 double bonds to chromium. And when you mix these 2 together, you're actually going to be in an equilibrium reaction. The equilibrium tends to favor the formation of this important intermediate. Excuse me. Where you have an oxygen from the alcohol now bonded to the chromium. All right, this is called a chromate ester. The book doesn't really describe how you form the chromate ester. I just want you to know that this is a really important intermediate for the Jones oxidation. And then in the next step, we're going to pull it out of equilibrium by treating it with water. Water, we know, can act as a weak base. So in this case, it's going to grab this proton, clamp down. We're going to actually kick off the chromium. During this reaction, we're going to end up with a carbon-oxygen double bond. That was that bond right here that we're forming. And then we're also going to kick off the chromium group that's essentially acting as a leaving group in this case. So this is the overall generic mechanism for the Jones oxidation that's covered in this chapter. All right, so now let's go back up and look at the example involving the primary alcohol. So with the primary alcohols, the key thing we said was we can't stop here using chromic acid. However, chemists don't like being told they can't do something. They want to figure out ways to solve problems like this. So let's take a look at an alternate where we could stop at the aldehyde. And this gets us into our second class of gentle oxidizers. All right, so the gentle oxidizers will avoid pushing a primary alcohol all the way to a carboxylic acid, which this was a pretty useful tool at the time. Today there's a lot more advanced techniques, but for right now this is going to be the main one that we're going to cover. And the reagent that's normally used is formed by mixing this reagent that has nitrogen in a ring system. This is called pyridine. We've used it a handful of times before, so for example, when we tosylated alcohols, we used pyridine as a non-nucleophilic base. Then we're going to use chromium trioxide, the same reagent that we used to form chromic acid before. And we're going to mix this with HCl. And when we do this, we're going to get an acid-base reaction. So the pyridine acting as a base is going to get protonated, and we're going to form a new type of chromium-based reagent, where in this case it has a negative charge. This reagent is called Pyridinium Chlorochromate. Let me zoom out a bit. However, pyridinium chlorochromate is kind of a mouthful to say, so everybody just refers to this as PCC. So if you ever see PCC, you should always think this is going to be a gentle oxidizer, not one of the really strong oxidizers that we saw before. So let's take a look at this in action. So let's say we do have a primary alcohol. Let me draw this a little bit nicer, where it looks like this. And we know we've got two hydrogens here, which makes it primary, right? Remember, the way to tell if an alcohol is primary, secondary, tertiary is to say, all right, this red carbon, meaning the carbon that the alcohol is bonded to, is only bonded to one other carbon. Therefore, this must be a primary alcohol. All right, so in this reaction, what we're going to do is we're going to react this with PCC. Sometimes you'll see a solvent listed below, like CH2, Cl2. Doesn't really matter in this case. If you just see PCC, it works just as well. And in this case, we said that it's not going to overshoot to the carboxylic acid. Instead, it's going to stop at the aldehyde. Which is kind of helpful. So if you think about it, now we actually have a variety of different techniques for making aldehydes. We can make aldehydes directly from an alcohol. We can make aldehydes from alkynes using that 9-BBN reagent followed by oxidation with hydrogen peroxide and base. Or we can make aldehydes by doing ozonolysis of alkenes. So we're adding to this toolbox. Now some students might ask, well, what happens if you use this with a secondary alcohol? So let's take this example where we have a secondary alcohol. If you treat a secondary alcohol with PCC, the oxidation reaction will still work, and you will end up with a ketone. So really this just stops after one step as opposed to pushing through multiple steps and getting to the carboxylic acid. The main thing to remember is with secondary alcohols, you don't have to use PCC. You can also use chromic acid. It doesn't really matter which one you use in this situation. So you can use chromic acid, which if you remember, there's a variety of different reagents we can use for chromic acid. So let's even just pencil them out. So option 1 for chromic acid would be CrO3, H2SO4, and acetone. That was one option we saw before. Or to make chromic acid, you can use sodium dichromate, which is Na2Cr2O7, followed by H2SO4 and water. In this case, you could use PCC or this one or this one. Doesn't really matter. You get a pick. All right. Now, I've mentioned before, both in lab and in lecture, that these are kind of old school reactions. Chromium-based compounds, especially chromium-6-based compounds, are really bad for your health and bad for the environment. So I did want to come up with a separate column called gentle and green. The good thing with these is I'm not really going to push you to know the mechanism, but I did want to briefly introduce them. So the first one is the Swern oxidation. So with the Swern oxidation, again, you can have something like a primary alcohol. So I'll just make a little note down here that this is a primary alcohol. And you can react it with COCl, and then in parentheses 2, followed by DMSO, followed by dichloromethane. And you also want to run this at cold temperatures. If you run it too hot, it doesn't really work well. And in this reaction, you can actually stop at the aldehyde as well. But if you notice, in this reaction, we're not using any chromium-based compounds, which is really a good solution in terms of avoiding using something that's toxic and bad for the environment. The other thing that you do get from this reaction is the byproduct from the DMSO is rather stinky. So it's dimethyl sulfide, which is really, really bad smelling. So you know this reaction works if it smells bad. So this one works, but it's stinky. There's also another one called the Des-Martin Pyridinium reaction. And in this reaction, same idea, where you could have a primary alcohol and we're going to use the Des-Martin Pyridinium reagent. I'm not even going to bother drawing that out, but I'll show you on the next page what that looks like. And same idea here. This will stop at the aldehyde. Now, neither of these reactions are perfect. First things first, this one's very stinky, which some people don't like doing stinky reactions. And then in this one, this is actually an explosive reagent, meaning you probably don't want to scale this up too large, otherwise you run the risk of actually having your reaction flask explode on you. There are more advanced techniques like the one we saw in lab. We oxidized a primary alcohol, like benzyl alcohol to benzaldehyde, and that was actually using very modern chemistry. So this chemistry is continuing to evolve as we're learning more and more about these reactions. All right. So these ones, I just wanted to make a note, are optional. You don't really need to know them. I just like showing them because it kind of bugs me in these newer books that they still tend to use these chromium-based reactions that aren't really that common anymore. If you are interested in learning more about these reactions, I've added a tab in our folder called Advanced Mechanisms. So if you're the type of chemistry student that really wants to learn about the Swern oxidation, you can kind of follow along with this mechanism that I've posted here. And then same thing with the Des-Martin Pyridinium. So I mentioned that DMP is kind of a complicated molecule to draw. That's what DMP looks like. And like I said, it is explosive, so you have to be careful when handling it. All right, so that's essentially the end of the chapter. You may notice that there's a section in the book called Oxidation of Phenols and Bioredox Reactions. I'm actually choosing not to cover that right now just because we don't have enough time. But if you are interested, there's a Khan Academy video that covers it as well. All right, so at the end of every chapter, they have these reaction maps. Remember that you made your own reaction map. You can go in and start adding in more connecting arrows. So for example, in this reaction map, the whole top half we've covered. In fact, we covered this reaction as well. Really, all of the new stuff that we've covered kind of lives down here. And even among that, a lot of it was still kind of review from last term. So try to add these into your reaction maps. Try to use flashcards to remember the difference between LAH and NABH4. Same thing with PCC versus chromic acid. It's really easy to mix those up, but the more you practice them, the easier it gets. All right, so that's where we're going to stop now. Like I said, the quiz on Friday will cover the alcohol chapter. However, if you do the skill builders for the synthesis chapter, you get one late lab report accepted. So you can do the skill builders for both chapter 11 and 12. They're really good review. All right, after this, what I'll do is I'll post a video on esters just so we can stay caught up. Make sure that you watch that video before Friday. During the quiz on Friday, there might be a hidden message in that video that will be on the exam just as a freebie set of points, just to tell that you watched the video. So make sure you don't miss those freebie points. All right, good luck studying, and let me know if you have any questions.